All right, kids. So this is how the journey will end. This is not at all how I expected this to play out when we started back in January. But this is the hand that we're dealt, and we're going to make the best of it. So here is the last kind of lecture that's going to tie together some different things. So when you look at intermolecular forces, that's one of those deals that we can't measure directly. It isn't like, hey, let's plug in the intermolecular force sensor into the LabQuest. So we have to find indirect ways to measure that. So one of the things that we look at is either vapor pressure or boiling point. So when you look at vapor pressure, how that's measured is that you take a sealed container and you put in a liquid. It might be water, ethyl alcohol, methyl alcohol, whatever this is. And it has to be sealed up so that the vapor can't escape. And so what's going to happen over a period of time at a particular temperature, some of these molecules are going to begin to break free. And what's going to happen then is you're going to put a pressure sensor in here, and you're going to keep track of pressure as a function of time. And what's going to happen is that pressure is going to increase until it begins to level off. So once it reaches a point of equilibrium, the pressure is going to remain constant. And the more vapor there is up above, the higher that line is going to be. Okay? Now, again, this is a dynamic equilibrium. So once this levels off, I don't want you to think, all the molecules have come to stop. All that's happening when this thing levels off is that the number of molecules that are going back into the liquid phase is equal to the number of molecules that are coming out of the liquid phase. So this is why this is called a dynamic equilibrium. So here's how this plays out. The higher the vapor pressure is, the weaker the intermolecular force, because what that means is that at a certain temperature, more and more of these molecules are able to break the bonds that hold it together as a liquid. So here's what we're going to do. We're going to look at four different molecules, and we're going to look at water, ethyl alcohol, sometimes called methanol, ethyl alcohol, sometimes called ethanol, and diethyl ether, which is this big complex string of carbons, okay? And it kind of makes this kind of bent shape here, okay? Now, so let's talk about what's going to hold these things together. So water because it has an oxygen and a hydrogen here, and an oxygen and a hydrogen here, okay? So that means this is going to have London dispersion forces because of the fact that it has an electron cloud. It's not going to have a lot of London dispersion forces relative to the other ones because of the fact that this is the smallest molecule. But it's also going to have a dipole moment, okay, because of the fact that's going to point towards that oxygen end. And it's also going to have the capacity to form two different hydrogen bonds. Now remember, and this will make sense later on, to have a hydrogen bond, the hydrogen has to be bound directly to either a nitrogen, an oxygen, or a fluorine. So since this hydrogen is bound directly to that oxygen, this is going to allow that hydrogen to bond to another oxygen in another water molecule to form a hydrogen bond. So water is going to have London dispersion forces, it's going to have a dipole moment, and it's also going to have a hydrogen bonding as well. Okay? So it's going to have all three of these. Now, if you look at methyl alcohol, 1 carbon, 3 hydrogens, and an OH group on the end. So this is also going to have London dispersion forces. This is also going to have a dipole moment because of that hydrogen. So it's going to have a dipole. And it's also going to have hydrogen bonding. But this hydrogen bonding won't be as strong as the water is because of the fact that this is just one hydrogen attached to that oxygen. Okay? So it's going to have hydrogen bonding, but not as much. Okay? Now, ethyl alcohol. ethyl alcohol is going to have London dispersion forces, and so far, this one compared to the methyl alcohol is going to have a stronger London dispersion force because of the fact that it's a more complex molecule. There's more of an electron cloud. It's easier to induce a dipole moment. Then you've got an OH group, so it's going to have a dipole moment, and it's also going to have hydrogen bonding. So the ethyl alcohol, on balance, is going to have the same hydrogen bonding as the methyl alcohol does. So the hydrogen bonding for these two is going to be the same. This is going to have an advantage in terms of London dispersion forces because it's a bigger electron cloud. And the dipole moment is going to be about the same. So the only difference between these two is the strength of the London dispersion forces. Now, then we get it down here to diethyl ethyl. Now, here's what you're going to be tempted to think. Oh, look, there's an oxygen, and it also has a hydrogen, so this should undergo hydrogen bonding. Okay, listen to me. This is not going to undergo hydrogen bonding, mainly because of the fact that that hydrogen is not bound to a nitrogen, oxygen, or a fluorine. So just because there's an oxygen here doesn't mean that you're going to have hydrogen bonding, okay? Because there's no hydrogens bound directly to this oxygen. So just because you have a hydrogen and nitrogen, and an oxygen and a hydrogen within the same molecule doesn't mean that you're going to have hydrogen bonding. It's only if that hydrogen is bound directly to that. And so in this situation, that isn't there. So this will have no hydrogen bonding. It might have a little bit of a dipole moment, but not much. But primarily, what's going to be the biggest thing here is going to be London dispersion forces. Now, relatively speaking, the London dispersion forces is going to be the stronger of all of these because of the fact that it has, without doubt, the largest electron cloud. But the London dispersion force is the only thing that it really has going for it because it doesn't have a dipole moment, it doesn't have hydrogen bonding, so this is the only thing that can hold it together. Excuse me, this is the only thing that can hold it together are London dispersion forces. Okay, so now let's look at boiling point. So the boiling point of water you all know to be 100 degrees Celsius. Methyl alcohol is 64.6. Ethyl alcohol is 78.3. Diethyl ether is 34.5. Now, allowing for the fact that room temperature is about 22 degrees Celsius, all of these are going to be liquids at room temperature because at 22 degrees Celsius, they're all going to be below that boiling point. Now, however, as you begin to warm them up, the diethyl ether is going to boil first. So if you had a mixture of these in a beaker and you began to boil it, your diethyl ether is going to boil off first. So because of the fact that it has the lowest boiling point, that's a reflection of the fact that it has the weakest London dispersion forces. Okay? And that's the only thing that it has. So this has the weakest intermolecular force, okay, and that's London dispersion forces, and it's the only one that it has, so therefore this is going to boil first. Now, the second, what's going to boil next, is going to be the methyl alcohol. Just like water, it has London dispersion forces, dipole, and hydrogen bonding, but it has the smallest electron cloud relative to ethyl alcohol. So this is why ethyl alcohol is going to have a slightly higher boiling point because of the fact that it's going to have a slightly larger London dispersion force because of the fact that it has a slightly larger electron cloud. Now you get into water. Water of all of these has the highest boiling point because it has the capacity to form two hydrogen bonds, it has a dipole moment, and it has that strong hydrogen bond. So if you notice, if you were to rank these, so water has the highest boiling point because it has the highest total number of intermolecular forces. Diethyl ethyl down here has the lowest boiling point because it has the weakest one. Now, over here, I have vapor pressure. Now, these are inverses of each other. So notice that diethyl ether by far and away has the highest vapor pressure. So if you put diethyl ether in a sealed container as a liquid, and then you measure that pressure on the top, over the top of it, that diethyl ether is going to have, without doubt, the highest vapor pressure because it's easiest for this to go. So if you imagine this being a room full of second graders, okay? So here's your diethyl timmies. There you go, diethyl timmies. So what this means is that these timmies only have like a tiny piece of Velcro that holds them together. So when it gets warm outside, these completely break apart very, very, very easily, which means that the pressure inside the room caused by this is going to go up really, really high because of the fact that these timmies aren't going to be stuck to each other, and they're going to be bouncing around all over the room because they have such a weak bond that holds them together. Now, in contrast to that, water, which has the highest boiling point, has the lowest vapor pressure. So these timmies, okay, they've got a lot of intermolecular bonds that hold them together. So therefore, not very many of these are going to separate. So this has the lowest vapor pressure, but it has the highest boiling point. Now, then you look at these two. Oh, here's methyl alcohol, okay? So it has a lower boiling point than the ethyl alcohol does, but it also has a higher vapor pressure. So again, this is why these are inverses of each other. So here's your general trend. As you decrease your boiling point, you increase the vapor pressure. And as you increase that vapor pressure and lower the boiling point, that means that you have weaker and weaker intermolecular forces. Now, if these intermolecular forces are strong enough, you can actually have something that's a solid at room temperature, okay, which is like graphite, for example. Graphite has such a strong intermolecular force that it's a solid at room temperature. Okay, so that's what I want you to see there. Now, so I've already sent out these lecture notes. So these are just some big trends on electronegativity, electron affinity, and first ionization energy. So electronegativity, this is kind of what, like the Robin Hood, okay, trend. This is the willingness to take electrons towards itself, but typically this is in the context of when an atom is part of a larger molecule. So if you look at I don't know, like let's say, for example, carbon, okay? So a carbon in a complex chain of molecules. So when we're talking about this electronegativity, we're talking about the willingness of these atoms to pull electrons into itself. Now, noble gases have zero electronegativity. It doesn't make any sense to talk about them because they're the noble gases. They have a full outer shell. But if you notice, and I've sent you this chart, so if you look at a chart of electronegativity, the noble gases have zero electronegativity. There's nothing listed there. But the halogens, so there's noble gases, they don't have any. But your halogens do have a high electronegativity because of the fact that they are willing to take in an electron. So it's kind of like, let's say you need 8 game pieces to be a winner. Well, the noble gases have all 8 game pieces, so they're not willing to take electrons or game pieces from someone else. Now, the halogens, which have 7 valence electrons, and they just need 1 more, they're very willing to take electrons to form and get all 8 game pieces. Okay. Now, electron affinity is similar to electronegativity, but yet it's not. So, electron affinity is the energy released, okay, this is going to be important, when you add an electron. So, let's say, for example, you have a fluorine atom, and it gains an electron and it turns into F1 minus, and then you're going to release some energy. So notice that your delta H here is a negative value. That's because of the fact that energy is going to be released. You're forming a bond between the fluorine and the electron. So basically, on an energy diagram, here's fluorine, here's F1 minus. So that's going to release that energy because of the fact that it's going to move to a lower energy state. Okay, so that's going to be important. Now, electron affinity, there is no electron affinity for the noble gases, mainly because of the fact that they're not going to gain an electron because they have all 8 gain pieces, so there's nothing to gain from that. Okay, now first ionization energy. This is kind of the opposite of electronegativity. So this is how much energy it takes to take away an electron. So on this one, these delta H's are positive because of the fact that you're in effect breaking a bond. So if you look at hydrogen, hydrogen's delta H is positive 1312. So that means that it's going to take energy to break this bond to take away this electron. Now, the noble gases, here's the thing where the noble gases kick in. Noble gases have extremely high first ionization energies, mainly because of the fact that they have all 8 gain pieces. They're the big winners. They're going to get the trip to Hawaii, although no one wants to fly to Hawaii now because of the coronavirus. But okay, hypothetically, you could fly in your own private jet. Okay, then maybe you take the trip. But the whole key to this is that they already have all 8 gain pieces. And since they have all 8 gain pieces, then it's going to take a lot of energy to take that away from them. So the noble gases, this is the only time you're really going to talk about noble gases in the sense that they are going to have the highest first ionization energy. Okay, now here's the last random thing that, and this kind of fits in with first ionization energy. So if they throw this in on the test, this isn't a difficult concept, but I don't want you to see this and flip out and go, oh my God, we've never seen this before. So it's called the photon electron spectrum. So what this does, it talks about how much energy it takes to remove electrons. So typically what you're given, I'm going to make this go away because I don't want you to think those are going to be written on there. So typically what you're given is a graph like this. So over here on the y-axis, you have the relative number of electrons, and this is binding energy, which is how much energy it takes to take those electrons away. So, and for example, this scale would be like 10 to the negative 18th joules. So it's not very much energy. So if you can figure out the code, these graphs are actually pretty easy to figure out. So let's say that, notice here that this is the smallest spike. So your smallest spikes are going to correspond to the S sublevel because your S sublevels only hold 2 electrons. These spikes are going to correspond to the P sublevel because those are going to hold on this scale 3 times as much, okay? Now if you had like a much bigger spike, that would correspond with the D sublevels, but generally they're not going to put those on there. Okay, I'd be surprised if they do anything with D sublevels, but that's the pattern. So basically what's happening here is that here's this nucleus, and here's these electrons that are closest to the nucleus. So because they're closest to the nucleus, they have the strongest force. So it's going to take that large amount of energy to take them away from the nucleus. So this would be like 1s2. So this is the energy needed to remove the 1s2 electrons. Now notice that we've got a gap, and then we hit the second spike. So this would be like your 2s electrons. They're further from the nucleus, okay? But, so that's going to take a little bit less energy because they're further from the nucleus and they don't have as much of an attractive force. Now, just in case they ask about it, the other reason that this is such like a big gap between these two is that you can get into what's known as electron shielding. Okay? So what happens with electron shielding is that these electrons in 1s are basically creating an interference pattern between the attractive force between the proton and these 2s. So I doubt seriously that you're going to have to know about electron shielding, but just in case, if you want to sound smart and they ask you about it, you can talk about that. Okay, so now this is out here in 2p. Okay, so this is my 2s2. This is my 2p6. And then I'm back here to 3s2, 3p6, and then 4s2. So if I add all these together, okay, so there's 8 plus 2, so there's 10. There's another 8, and there's 2, that gets us to 20. So this is the element calcium. So even though they don't directly tell you this, and this problem came off of last year's AP test. So if you look at last year's AP test, this is the exact problem that they had. And so here's all you need to know about this photon electron spectrum, is that the smaller spikes are going to correspond with the S sublevels, the bigger spikes are going to correspond with the P sublevels. The further the way you get from the nucleus, the less energy it takes. So this is somewhat reflective of like first ionization energy. So first ionization energy is how much energy it takes to remove that single electron. So this would be out here with, like, say for example, calcium. So this is this energy to remove those outer 2 valence electrons. Now, and I know you all have done these calculations before, but again, this is just a quick review. So don't forget the energy of light is either h times frequency. C equals the speed of light, which is wavelength times frequency. So if you solve for frequency, you get C over lambda. So the energy of a photon can also be written as hc over lambda. So what they might say is like, okay, hey, you know, what's the wavelength? I think this is how they played this. They'll say, okay, what's the wavelength of light that's needed to eject those electrons from calcium? And so you'd come in here and go, oh, lambda then would be hc over E, and you take that energy and you put that in here, and then you can find the wavelength of that light. So, okay, that's it. So that's the last lecture. It's kind of sad. Anyway, thanks for sharing the journey, and the test is going to be on Monday. This is kind of the last kind of hoorah. I'm going to send out the review. We're going to have the meeting at 11:30. It's now like 11:10. I'm going to have time to get something to drink. So that's the story, kids. And